Hello and welcome back. In this video, we're going to be looking at calculating molar mass. In a previous video, we talked about what gram atomic mass is versus molar mass. And I told you in that video that molar mass is a term that is most often used when referring to the mass of elements or compounds. But by strict definition, molar mass is the mass of a compound given simply in terms of grams per mole, regardless of whether that compound is a formula unit or a molecule. But for the purposes of calculating molar mass, we have to kind of redefine that definition to where now we're going to think about molar mass as being the sum of the gram atomic masses of each element in the particular compound. And when you look at a compound and you're looking at that formula, if you see subscripts on it, those subscripts denote the moles of each element that's present in 1 mole of that compound. So for example, if we've got magnesium chloride, MgCl2, that formula indicates that for every 1 mole of the compound, MgCl2, there's 1 mole of magnesium atoms, and there's 2 moles of chlorine atoms. We don't write a 1 as a subscript, so that's why it's simply MgCl2 rather than Mg1. Or is actually calculating molar mass. What you need to do is first off list the elements that are present within the compound elements out to denote how many of each type of element is chloride. We list out magnesium, then chlorine. There's 1 magnesium, 2 chlorines. After you've denoted the number of each element present, the gram atomic mass for each element. For that, we're going to go to the periodic table. After you've listed out the gram atomic mass for each element, you're going to multiply the number of each element by its own unique gram atomic mass. Once you've done that, we're simply going to add those products together, and then molar mass always has units of grams per mole. So let's go on and take a look at a couple of examples. Okay. So first off, periodic table. This is where we're going to end up finding our gram atomic masses. Okay. Again, that is going to be these masses that are in the corners that we looked at in the last video, but we're going to put units of grams per mole on it. So let's look at the example of magnesium chloride that I've already given you. So when we're looking at magnesium chloride and we go through these rules, again, the first thing that I want to do is list the elements that are present. So I have magnesium. Get my pen pulled up. I have magnesium and I have chlorine. The next thing I want to do again is denote the number of each type. So magnesium with that unwritten subscript of 1 tells me I have 1 magnesium. Chlorine with the subscript of 2 tells me 2 chlorines. So I've denoted each type. The next thing I'm going to want to do is denote the gram atomic mass for each element. Again, that's going to come from our periodic table. So for magnesium, I see 24.305. For chlorine, 35.45. So magnesium, again, is that mass at 24.30, and that would be units of grams per mole, because it is the gram atomic mass. 2 chlorines, each at 35.45, again, units of grams per mole. And you can abbreviate mole as MOL. You don't actually have to put the E on the end of it. Now that I've denoted those gram atomic masses, I'm going to multiply each number of, or the number of each type of element by its gram atomic mass. So 1 times 24.30 is 24.30. And this value of 1 is actually, again, telling me 1 mole. So if we want to think in terms of units, units cancel, and I would have 24.30 grams of magnesium within that compound. Same thing with chlorine. That's technically 2 moles of chlorine. So unit-wise, moles would cancel. And 2 times 35.45 is 70.90 in the units of grams. So now that I've multiplied, I would need to add those products together. So when I add the 24.3 plus the 70.90, I get 95.20, and that would be grams of magnesium chloride, my compound. And again, because this is done in terms of grams, that would be per 1 mole of magnesium chloride. So this would be the molar mass of magnesium chloride. Many times you'll simply see it written, though, as 95.20 grams per mole, where you can then either put the substance behind it or simply say that the molar mass of magnesium chloride is 95.20 grams per mole. So that's a fairly straightforward example. Right? So let's look at one that's a little more complex. C6H12O11. So again, we're going to follow by these rules. I'm going to list out my elements. I have carbon, I have hydrogen, and I have oxygen. Secondly, I'm going to put down how many I have of each. So according to the formula, I would have 6 carbons, 12 hydrogens, and 11 oxygens. The next thing to do is to find their masses on the periodic table. So I'd go back to the periodic table, and carbon is 12.01, hydrogen is 1.01, and oxygen is 15.99. So carbon, 12.01. Again, that would be grams per mole, but a lot of times in working these problems, we don't worry about the units at this point. Hydrogen, 1.01, and then oxygen, 15.99. I would now multiply. So 6 times 12.01 gives you 72.06. And that would be grams of carbon within 1 mole of this compound. For hydrogen, 12 times 1.01 would give you 12.12. And then for oxygen, 11 times 15.99 would give you 175.89. Lastly, we would add these up. So 72.06 plus 12.12 plus 175.89. When you do that, you would get 260.07. And then because it's molar mass, and remember, molar mass always has units of grams per mole, we would simply put gram per mole, and that is the molar mass of C6H12O11. Let's look at another one. This is a little more complex in that we're now involving parentheses. When you see parentheses, what this means is that this compound, there's 2 of this OH group for every 1 beryllium. So when we list out our elements and then tell how many there are, we have to, in essence, factor through. So I've got beryllium, I have oxygen, and I have hydrogen. According to the formula, there is 1 beryllium. Then for oxygen, because there's 2 of this grouping and there's 1 hydrogen or 1 oxygen per the grouping, if we factor through, that would tell me that I actually have 2 oxygens total. 1 oxygen in one of the OH groups, the second oxygen in the other OH group. Same thing with the hydrogen. I'd factor through. These values are going to get multiplied by the gram atomic mass of the elements. So if you go to the periodic table, you might recall we've looked at beryllium previously. It has a mass of 9.0122. And in most molar masses, we're just going to go to the hundredths place. So in other words, 2 decimal places. Oxygen, we looked at previously, is 15.99, and hydrogen, 1.01. We now multiply these together. So 9.01. 2 times 15.99 is going to give you 31.98. And then for hydrogen, 2.02. Then we add those products up. So 9.01 plus 31.98 plus 2.02. And we get a molar mass of 43.01 grams per mole. So this is how you would incorporate these parentheses. Simply factor through. And you can have parentheses on either the first component or the second component, or you can have them on both components. Either way, you're going to take and factor through that value to each element that's within that set of parentheses. So for this particular compound, ammonium carbonate, I'd have nitrogen, hydrogen, carbon, and oxygen. Nitrogen, I would have 2 times 1 for 2 total nitrogens, 2 times 4 for 8 total hydrogens, then just 1 carbon and my 3 oxygens. Those are each going to get multiplied by the gram atomic mass that you would look up on the periodic table. If you look up nitrogen, you'd find it to be 14.01. Hydrogen again, 1.01. Carbon, 12.01. And oxygen, the 15.99. Multiply these all together. So 2 times 14.01 gives you 28.02. 8.08, 12.01, and then 3 times 15.99 gives you 47.97. Then add those products. So 28.02 plus 8.08 plus 12.01 plus 47.97. We find a molar mass of 96.08 grams per mole for ammonium carbonate. Final example for you, and if you can do all of these that we've done up to this point, this one shouldn't present any difficulty for you. It looks a little difficult, but in reality, very simple if we just follow those same sets of rules. So I have mercury, I have phosphorus, and I have oxygen. So for mercury, if I factor through, I'm going to have 6 mercuries. For phosphorus, 2 times 1 will give me 2 phosphorus, and then 2 times that 4 gives me 8 oxygens. Then I would look up their gram atomic masses. For mercury, that is 200.59. Phosphorus is 30.97. And then oxygen are 15.99. Multiply each one of these. 6 times 200.59 will give you 1,203.54. 2 times 30.97 will give you 61.94. And 8 times 15.99 gives you 127.92. Then add all these up. So 1203.54 plus the 61.94 plus the 127.92. And I'd have 1,393.40 grams per every 1 mole for the molar mass. Now, here's one aspect that we haven't talked about yet, but it's important that you do understand. When we calculate these molar masses, if I go all the way back to magnesium chloride, this molar mass of 95.20 grams per mole means if I go into the lab and I pour out 95.20 grams of magnesium chloride onto a balance, I would have exactly 1 mole of magnesium chloride. If you remember from previous video, if I have 1 mole of magnesium chloride, I would have 602 sextillion units of magnesium chloride. Or within that many units of magnesium chloride, I would have a specific number of magnesium atoms, and I would have a specific number of chlorine atoms. So we use molar mass to be able to start theoretically counting the number of atoms we have within compounds through the mole concept. And again, as I mentioned at the beginning of the first video, when you get into stoichiometry, molar mass is of the utmost importance because it is how we as chemists are able to theoretically count the number of atoms that we have sitting there on the balance, the number of atoms or molecules, formula units, ions, whatever it is we're working with. It's how we count how many things we're actually using up in a reaction and how many things we're producing within that reaction. And that's extremely important to chemistry. So hopefully all this had made sense to you. If not, feel free to leave a comment and I'll get back to you as soon as possible. Thanks and take care.